So today's session is about Wi-Fi 6 or 802.11ax and the new features that have been introduced in this standard extension. Before we jump into today's topic, let us quickly summarize what we presented in the last session. So in the last session, we covered some of the standard extensions that we did not get a chance to cover in the part 1 of this course. So specifically, we talked about 802.11h, which is about DFS and transfer power control. DFS is all about using certain channels in the 5 gigahertz band that are allocated for radar communications. But the government organizations have allocated those channels for unlicensed use with the condition that you have to follow certain rules when you use those channels. And DFS is all about how do you make sure you follow those rules to make sure that you're not interfering with critical radar communications. So we talked about what those rules are and what we need to do to comply to them, and how to detect a DFS signal and how to move off of the channel, how to stay off of the channel, how the various standards bodies work, and what kind of testing needs to be done to qualify for a DFS certification. We talked about 11K in pretty detail. Basically, we talked about which is about radio resource management, especially in enterprise Wi-Fi, where you have lots of access points deployed in close proximities with each other in high dense environments. It is very important to make sure you manage your radios properly, and that includes RRM features, but it also includes helping the clients make the decision of which particular access points to choose. In a residential environment, we all know that we only have one access point to connect to, so we don't have any other choice. We just connect to the AP that we have in the house. But in an enterprise environment, the station has a choice to connect to many different access points, and so how to pick the right access point, how to roam at the right time, is what 11K is about. 11K allows the clients to actually get important information about neighboring access points without having to go off channel and scan. They can get the information from the current access point itself. We talked about it in detail. We talked about auto channel selection and some proprietary implementations of auto channel selection algorithms by various vendors. And we talked about 11V, which is about wireless network management. And that is specifically used again in assisting the devices to pick the right network to connect to, especially in a heavily loaded environment. You need to make sure all the devices or all the stations are connected to the optimal access point so that everyone basically is using the medium the most efficient way possible. In some cases, clients don't behave as expected. They're very sticky. They might not pick the right access point to connect to. There might be a much better access point right next to it, which is giving you a very good signal, but the client might decide not to move. In that case, the network can assist the client in making the decision, and that is where the network would manage basically the devices themselves. And 11B has certain features like BSS transition and other things where the access point can decide for the client which device to which access point to connect to. And so that's 11V. We talked about 11R in detail for fast roaming. So 11K and 11V are about helping the stations make a decision of when to roam and where to roam to. So when to roam is important. You cannot try to roam too fast. You cannot try to wait too long to roam. So you need to make the decision at the right time. And you also need to pick the right access point to move to. So when to roam and where to roam to are basically 11K and 11V. But once the roaming decision has been made, how fast can you roam and how secure can you keep the connection handover is what 11R is talking about. 11R is going to cover basically fast, secure roaming, where you're making sure the roaming is secure and also fast. So we talked about that in detail. So anyone who missed that session, the recording should be up on our website now, so you can go and watch that. And anyone who's joining us for the first time, this slide will give you access to our course webpage. There's a detailed course webpage which has all the material, videos, and everything from part 1 and part 2. And if you're not registered, you can use this registration link. And you can also join the WhatsApp group if you want to get updates on WhatsApp. Okay, so jumping into today's session. So going back to the bigger picture, we are going to talk about Wi-Fi 6 right now, but to set the context, Wi-Fi, of course, has been evolving over several generations, all the way from Wi-Fi 1 A11 802.11 to APG to 11N to 11AC, AX, and so on. So this slide shows from Wi-Fi 4, and we have Wi-Fi 4, which is 11N, and Wi-Fi 5, which is 11AC, which can be considered in some ways the base standards because they have a set of features that we've already talked about extensively in part 1 of this course. So we didn't really get a chance to talk about the new features that have been introduced as a part of the newer standards, Wi-Fi 6, 6E, 7. And this session is going to cover the new features that have been introduced in Wi-Fi 6. And next session, we're going to talk about Wi-Fi 6E, and then the one after that, we'll talk about Wi-Fi 7. So, so today we're going to introduce and talk about the new things that have been added in Wi-Fi 6. Before we go and discuss that in more detail, we have to remind ourselves of the backward compatibility problem that has been there in Wi-Fi for a very long time. So every time we have a new standard extension, we're all very excited. Okay, 11AX came and it introduced 1024 QAM. Now you can get to 10 gigabits per second throughput. So we're all excited about it. Access points are released. You can see on the box it says it can do 9 gigabits per second, 4 gigabits per second, whatever throughput. But is that the reality? And we have discussed this many times, that that's really not what happens, because every access point and every new standard extension that has been released has to be backward compatible with the legacy devices, because the devices themselves may not evolve as quickly as the access point. So we might get one new technology every 2-3 years, but people may not update the devices for a long time, and they will be using previous generation devices. So backward compatibility is important, and backward compatibility creates problems. So to illustrate that with a simple example, let us say in your town or in your city you have the first road ever, and let's say you're in the 1960s, and this is a dirt road, right? So you have a road which you can travel, and let's say because it's a dirt road, you can travel maybe at 40 kilometers per hour at your top speed. So now you're excited that you have a road and people can travel at 40 kilometers per hour. But now if you look at the vehicles that are going to travel this road, they can come in many different shapes and sizes. So maybe you have a car which is a 1960s car which can travel at 40 kilometers per hour speed. So it can use the full speed that is available on the dirt road. But the same road is also shared by maybe a horse carriage or maybe some other vehicle that can travel at a much lower speed. So if that particular vehicle is be traveling on the road, then the car that can travel at full speed cannot really use the full speed of the road, because it has to kind of fall down to the lower speeds. And so which means that you're not able to actually use the full capacity of what the road can offer because the road has to service many different types of vehicles. Now, if you fast forward another 20-30 years, now the same road became, let's say, gravel road. It's better. Now you can travel at 100 kilometers per hour. You're very excited, and someone actually even made a car that can travel at 100 kilometers per hour. So you're very excited that the car can travel on the road at 100 kilometers per hour speed. But then again, you have the same backward compatibility problem. So there are these old devices from the 1960s that cannot actually travel at 100 kilometers per hour. So they will also be using the road. And when they are using the road, they are taking up time on the road, which doesn't allow your high-end car to travel at its full speed. And then again, you fast forward. Now you, let's say, have a racetrack, and now you can travel at 200 kilometers per hour. Now you have the same problem. Someone might have introduced a car that can travel at 200 kilometers per hour, but then you still have to deal with the same backward compatibility problem. So ideally, if you're operating in greenfield mode, where you don't have to worry about backward compatibility, then basically you'd replace all the cars on this road with this high-speed car that, and then everyone can travel at 200 kilometers per hour speed, and now you're using the full bandwidth. So this is a standard backward compatibility problem that Wi-Fi has to all its generations, right? And that continues to be a problem with 11AX as well. Even though 11AX promises very high data rates, because of backward compatibility, the overall throughput that can be achieved is quite low. Okay, so coming to 11AX, what are the new features in 11AX? So 11AX, just like the previous standards, allows you to go faster. Like now it's that you went from the gravel road to basically a nice, much better road, right? So because you're getting more speeds. So Wi-Fi 6 allows you to transmit at a much higher speed by using higher order modulation rates like 1024 QAM. But Wi-Fi 6 is also about not just about speed, it's also about efficiency. So traditionally, what the standards bodies have done is every time they release a new standard, they have developed faster and faster access points. And the assumption is that there are only like a small number of client devices in your home or in your office. And so if you can increase the bandwidth of an access point, and if you can release a station that can actually also transmit at the higher bandwidth, then you get better speed, right? And the assumption was still that you will only have a small number of devices that are being used by the that access point is serving. But that is not the case in the modern world. In a typical home now, we have 20, 30 Wi-Fi devices, and in a typical enterprise, you could have 50, 100 Wi-Fi devices. And they're not just the standard laptops and smartphones. They are also the wireless printers. They are the vacuum cleaners. They are the robotic devices. They are wireless scanners, medical equipment, all kinds of IoT devices that run on Wi-Fi. And these are smaller devices. They need much lesser bandwidth. It's not about throughput for them. It is about how many devices we can support, and can it support, can we transmit data at low latency. So latency is more important than throughput for many of these lower end devices, because they are carrying important applications. So if you have a patient monitor which is measuring vital stats from the patient and transmitting that information over Wi-Fi to the doctor, that information needs to be sent very quickly, and you cannot really have high latency there because it's real-time information. If you're doing gaming, and if you're doing real-time gaming, or if you're doing some form of AR, VR application, latency is very important. And so what the standard is trying to solve is not just the throughput problem, but it's also trying to solve the scale of devices and also the latency problem. So now you should be able to serve a lot more devices and make sure that none of them are facing very high latency, right? So it's not just about one client's throughput, it's about all these other things. And that is really what Wi-Fi 6 is all about. It's about basically getting higher efficiency. And there are some new methods or technologies like OFDMA and multi-user MIMO that have been introduced to help with that process. We're going to talk about that in detail in this session. Okay, so the first new thing in Wi-Fi 6 is higher order modulation rate. Every time we go to a newer standard, we just want to pack more and more bits per symbol, and we're using higher and higher modulation rates. So Wi-Fi 5 11AC went up to 256 QAM constellation or modulation rate, and Wi-Fi 6, which is 11AX, now goes up to 1024 QAM modulation rate. Right. So the higher order modulation rate, we explained this in more detail in the part 1 of this course. There is always a trade-off. The higher order modulation rate gives you more bits per symbol. It gives you higher spectral efficiency, which means it gives you much higher throughput. But the trade-off is that the communication is not reliable, and you need a much better signal quality and a much better signal-to-noise ratio to maintain communication at that higher order modulation rates. So what that means is, if you have 11AC AX access point, then and if you're transmitting 1024 QAM, maybe within like 2 meters or 3 meters or 5 meters, and if you have line of sight, then you should be able to successfully communicate. Then the signal-to-noise ratio is high. There is no interference, co-channel interference. Then you should be able to make the full use of the higher order modulation rate and get the full throughput. And as you can see in the chart on the left-hand side here, the receiver sensitivity needs to be much higher for 1024 QAM, about -45 dBm. While with BPSK, you can go all the way up to -85, -90 dBm. So basically, your signal-to-noise ratio and the quality of the received signal needs to be really good to be able to use these higher data rates. So even though the box says you can achieve like 9.6 gigabits per second throughput or something, there are lots of caveats and there are lots of conditions under which you can achieve that. So 11AX introduces two new MCS rates. We have up to MCS 9. If you remember the MCS table from the previous sessions, we have up to MCS 9 that goes to 6 QAM with the 11AC. 11AX added MCS 10 and MCS 11 that is 1024 QAM at 3/4 coding rate and 5/6 coding rate, and that allows you to basically achieve even more throughput, basically. So that's 1024 QAM, and this is purely about speed and about better throughput, right? That's what this feature is added for, and every new standard needs to keep going up and up to actually support more and more speeds. But as we said, 11AX is not just about speeds; it's also about higher efficiency and also increasing the capacity of the number of users that can simultaneously use an access point. So let's say after 11AC standard, typically in an enterprise environment, let's assume that you're going to have 20-30 clients connected to an access point. In 11AX, the idea is that you should be able to connect to 100, 500, even 1,000 Wi-Fi stations to a single access point, because it supports technologies like OFDMA that would allow you to simultaneously serve many clients at lower bandwidths, right? And that was the whole idea behind Wi-Fi 6. So to illustrate the concept of something like OFDMA, which is a new concept in Wi-Fi 6, I just wanted to use a simple example. So let's say you have a 40 megahertz channel, and you're using the 40 megahertz channel to do OFDM transmission. So the channel here is represented by let's say a road. Right? Now you have this vehicle that is of a certain size, and it is carrying certain payload. And with time instant 1, because the road is has a certain amount of width, you can actually build a certain size of vehicle, and then you can send a certain amount of payload on that particular vehicle, right? So in time instant 1, you can do that. In time instant 2, maybe another payload from another device can be carried in time instant 2, and maybe in time instant 3, you can carry another payload in another device, on another vehicle. But now let us say you have wider channels, like 80 megahertz. So that means the road is wider. Okay. So now what you can do if the road is wider is you can build a bigger vehicle. Right? So now you build a much bigger vehicle that can use up the entire road because the road is much wider. And now because the vehicle is much bigger, you can send twice the amount of information on a single vehicle, right? From a single user in time instant T1, right? But again, here we're assuming that as you're increasing the size of the road, which means you're making the AP faster and faster, you have the devices also needing the same amount of bandwidth. So for example, let us say this is a wireless TV and it is doing high definition 4K video or 8K video or something like that. Now there is a bandwidth requirement. So of course it wants to send more information, and so it will use the entire bandwidth. But not all devices are going to stream 4K, 8K video. They might be an IoT device. They might be like a printer or a scanner or a small, basically some form of home media device that doesn't really have that amount of data transmit. So in that case, it uses a smaller vehicle and sends lesser amount of information, and it is not using the entire road. Some part of the road is being wasted, right? In time instant 2. Now, if you have even wider channels, okay, so now you are assuming that you have even higher speed. Now you can build a even bigger vehicle. Let's say you're transmitting some form of a 8K video stream that needs 200 Mbps data rate, something. So you can build a bigger vehicle and of course send a lot more information from that particular device. But again, you still have the same problem. There are other devices that really don't need that amount of bandwidth, but they have to use the entire spectrum. They have no other choice, and which means a lot of the spectrum is being wasted. So you're much better off splitting the spectrum into 2 separate access points. So like, for example, most of these access points, modern access points, use 80 megahertz and 160 megahertz channels. And so when you're using 160 megahertz channel, then if your transmission only requires a small amount of data, then you're wasting a lot of spectrum. So this is how normal OFDM works. But how does OFDMA work? The OFDMA works in an interesting way, right? So, okay, for example, you have 160 megahertz wide channel, which means you have a very wide road. So let us say there is one device that requires all that bandwidth, and so you're using a much bigger vehicle and you're sending a lot of information. But the second time instant, let us say there are 2 other devices or 3 other devices that have lesser amount of data to send, right? And they don't need the full bandwidth. So now what you can do is you can split the road into smaller channels. And for example, here we said, okay, these 2 parts of the road are one channel, this is one channel, this is one channel. So now you're breaking down that into 3 channels, and now since this is a wider channel, the device that needs more bandwidth can transmit in this channel, right, or travel on this road, and then this road can be used by a device that needs lesser bandwidth or a smaller device with a lesser payload, and this could be used for another device. Now you have 3 devices that are transmitting simultaneously, and they are not getting, if you add all this throughput within one time slot, it is the same as here. But now, so your net throughput is not increased. Like the net throughput, maximum throughput you get is still the same. But now you're able to serve multiple devices at the same time, especially devices that need lesser throughput. So what is this doing? It is solving a very basic problem. It is allowing multiple devices to access the medium at the same time. And through that process, you're able to serve more devices. And because of that, you're able to reduce latency. Because there are multiple transmissions happening at the same time. So that means that the amount of time this device has to wait to get access to the medium and transmit is lower than this case. And hence the latency will be lower. So you are serving more devices and you're decreasing the latency, which are the 2 main things that you want to solve in OFDMA. So same example, let's say in time instant 3, again, maybe there are 2 devices, they have medium amount of traffic to send. So somehow they can say, okay, I'm going to use these 2 top slots or parts of the road to transmit, and then the second device will use the bottom part, right? And this can dynamically change based on the bandwidth requirements in the wireless LAN cell, because the amount of data that has to be sent and received to any station or multiple stations, that can keep changing over a period of time. It's not fixed. So as that keeps changing, the AP and station can negotiate that, and then based on the bandwidth requirements, they can split the available bandwidth into smaller chunks and transmit in those smaller chunks and achieve simultaneous communication. So that's the basic concept behind OFDMA. Now, if you look at how that works in basically in a diagram here, and if you look at talk about the Wi-Fi language here. So this is on the top is where you have the classic OFDM, the x-axis being time, and the y-axis being frequency. So over time, what you're doing here is all these lighter parts are where the medium is not being used, and that is the contention, and also some form of management frames and so on. So, and then after that, each transmission is serial. So which means that the blue is one device transmitting and it's using the entire frequency band. Then you have another device that is using the entire frequency band, irrespective of how much data they have to send. Each device has to transmit serially, and it will use the entire band to transmit, just like the road example that I gave. In OFDMA, you can achieve simultaneous transmission. Device 1 can transmit in this frequency slot. Device 2 can transmit in this frequency slot. Device 3 can transmit in this frequency slot simultaneously. And then when you get the next transmission opportunity, maybe a different set of devices will transmit, and with different amounts of channel bandwidth used, right? And each transmit opportunity that can vary, and that is how OFDMA really works at a concept level. Okay, so let's dig deeper into basically how the technology actually works at a Wi-Fi protocol level, right? So, before we do that, we need to kind of refresh our memory on how the concept of OFDM, right? So this is one of the slides I took from one of the sessions from part 1. So if you look at FDM, or frequency division multiplexing, so information or data is carried simultaneously on different frequencies, and that is how you get multiple access, by transmitting on different frequencies. So that is normal FDM, frequency division. What OFDM does is it allows the user to actually send information in smaller subcarriers or smaller chunks of frequencies, and it allows to squeeze those frequencies in the frequency domain to actually get more spectral efficiency. The idea here is each information or subcarrier is using a certain frequency, and then the next subcarrier is overlapping with the frequency from the previous subcarrier. And it is done in such a way that it is orthogonal. So, for example, the signal 1, which is red here, is being transmitted, and then it's transmitted in such a way that the peak of that signal coincides in time with the null of the other signals. And so, when the symbols are overlapping, they can still overlap, but they can, but at the same time they can avoid interference. Okay. And that is called what we refer to as orthogonal frequency division multiplexing, where the multiplexing is done in an orthogonal way, and that allows you to squeeze more data subcarriers into a basically a chunk of frequency. So while if you have like this amount of frequency required to send these 6 subcarriers, if you squeeze them like this and transmit them in an orthogonal way, then you're saving so much bandwidth, right? So that's basically what OFDM is. We talked about that in detail in one of the previous sessions. So that is classic OFDM, but with 11AX, there have been some changes made in OFDM itself. Right? So the 11AC OFDM was using basically, if you take a 20 megahertz wide channel, they were dividing that 20 megahertz wide channel into 64 subcarriers, right? And the subcarrier spacing was about 312.5 kilohertz. So what is subcarrier spacing? That is the space between each subcarrier, this space here, right? So that space was 312 kilohertz. So with 11AX, what they did is they squeezed it even more, and they said, okay, we don't really need that amount of spacing in subcarriers. Let us go down, basically divide that by 4, and then they changed the subcarrier spacing to 78, right? Which means that the subcarriers are even closer in the frequency domain. And that allows us to pack more data into the same 20 megahertz spectrum. So while 11AC can do about 64 subcarriers, now 11AX can do 64 times 4, 256 subcarriers within the same 20 megahertz channel. Okay. So now you're able to send like 4 times the amount of information. And then basically the symbol duration has also been increased. From 3.2 microseconds. Symbol duration is how long the signal or the symbol is being transmitted. That also has changed from 11AC to 11AX. Right. So these are some of the changes, and so that allows you to do up to 256 subcarriers in a 20 megahertz band in the case of 11AX. Another change with 11AX is the guard interval. So the guard interval is basically the interval between the subcarriers. So longer the guard interval, the lesser you are prone to have intersymbol interference. So long guard intervals are normally used in long range communication and in communication where you have a lot of multipath. So the longer the guard interval, the higher the intersymbol, the delay spread you can have, and you are more prone to save yourself from intersymbol interference. So longer guard interval, more overhead, but lesser interference. So with 11AX, they even added even more longer guard intervals, like 0.8 microseconds, and then 1.6, and then 3.2 microseconds. So that increases the overhead from a guard interval point of view, but the overall efficiency is not going to be hurt because even though the guard interval is increased, the symbol time is also increased, and the intersymbol gap is also decreased a lot. So that overall that compensates for the loss in efficiency. So these are some of the changes. To kind of summarize, the subcarrier spacing has decreased in 11AX. The symbol duration has increased, and also the guard intervals also have been changed, have been increased in the case of 11AX. Now all of this is still OFDMA. We didn't even talk about OFDMA yet. Just the changes in OFDM between 11AC and 11AX. So now let us jump into the concept of OFDMA. So what are we doing with OFDMA? Right. So as I explained the roads and the lanes example. So let us take the simple example of a 20 megahertz wide channel. Now, of course, this applies to 40, 80, 160, 320 megahertz. But let's forget about all of that for now. Just to keep it simple, let us assume a 20 megahertz wide channel. So the 20 megahertz wide channel in normal OFDM, let's say this AP is transmitting 20 megahertz wide channel. Only one client can transmit in the entire 20 megahertz channel. In the example I showed you, if there is a road, the entire road is used by one vehicle. Right? So they could be like 5 or 10 other devices, but they all have transmitted 20 megahertz channel band. So with OFDMA, what we're doing is we're saying, okay, the 20 megahertz bandwidth can be one one chunk, or what we refer to as one resource unit, that uses basically all the subcarriers or all the tones. So we're also going to use the word tones instead of subcarriers and interchangeably. So all 242 tones, if you remove the pilot tones and things like that, you'll get 242 tones available for data information. So all of them can be used as one resource unit by one device. Right? That is the standard communication, right? OFDM. But for OFDMA, what you can say is now you have an option of saying, oh, I want to break this down into two resource units of 160 tones each. Right? So now you're able to do two simultaneous devices transmitting at lower bandwidth, but then they can both transmit simultaneously. It's like the highway example I gave you. Now you can use 2 lanes for one vehicle and 2 lanes for other vehicle across a 4-lane highway, right? So now you have that advantage, right? Or you can say, I want to have 4 resource units. Each of them will be 52 subcarriers or tones, right? So now the bandwidth is even shorter, but now you're able to have 4 devices communicate at the same time. Or you can go even lower and say, I want to have like, let's say 8 resource units with 26 tones each, and then you will have 8 simultaneous communications, even lower bandwidth. So let's assume that you have your ultra high definition TV that is transmitting at 8K, and it might decide to say, I want to use the entire 20 megahertz band, so I want all 242 subcarriers or tones for my communication. And next, in the next transmission opportunity, there might be like some lower end devices like your doorbells or your wireless cameras or your Alexa or something like that is sending lesser amount of data. And then they might decide, okay, I don't need all the tones, and I'm going to use 26 tones, and I'm going to have like 7-8 devices transmit simultaneously or receive simultaneously. So that flexibility is provided by OFDMA. That's where you get the multiple access from, right? So within a 20 megahertz channel, you can get basically up to 9 simultaneous users if you're using 26 tone RUs. So if each RU or resource unit is 26 tones long, then you get 9 users simultaneously. If you're using 52 tones, that means your bandwidth is wider, but then you'll only get 4 simultaneous users. And if you're using 166 tones, then you get 2 users. And if you're using all 240 tones, then you'll only get 1 user in the 20 megahertz band. And now you can extrapolate that to 40 megahertz, 80 megahertz, and 160 megahertz. So the most you can get is if you're doing 160 megahertz wide channels, and you're using the lowest number of tones, 26 tones in an RU, then you can get up to 74 simultaneous users communicating with the AP at the exact same time, which is pretty mind-boggling. So there are 74 devices all sending information at the same time, or receiving information at the same time from the AP, which is in theory it looks very nice, and practically it's almost impossible to implement. But it's a cool thing to know, right? That the standard allows for these kinds of features. So that's the concept of resource units. So now let us see how the downlink OFDMA frame exchange process happens. And downlink meaning AP is transmitting to multiple devices in a wireless LAN cell. So there is the AP, and then let's assume that you have, for simplicity basis, you have 4 stations that are around the access point, right? Now we have to remember that this only works with the APs that will support OFDMA, and also the stations have to support OFDMA. If you have legacy devices that don't support OFDMA, then they are not going to participate in this exchange, and they will wait for their own transmission opportunity. Remember the example I gave for backward compatibility. You have a very fast road, you have the fast car, but then there is a horse carriage, right? And there will be those horse carriages that will slow you down. But within a transmission opportunity, if you are doing OFDMA, then all devices that are using the transmission opportunity should support OFDMA, APs and stations. And the devices that are not doing OFDMA will wait for a different transmission opportunity where you don't have to do OFDMA. Right? So that we need to make sure that's understood. Okay, so let's assume a simple scenario where we have an AP and there are 4 stations that are all capable of doing OFDMA and want to do OFDMA and send information. Okay, so now the packets are arriving to the AP, and these packets need to be transmitted from the AP to all these 4 stations, and the AP has all these frames or data buffered that it needs to transmit. Okay, so now the AP, since it has the information data to all these stations, it knows how much data is buffered for each station. So let's say station 1 has very little data, station 2 has a lot of data, and station 3 has a medium amount of data. That information the AP already knows. So what does the AP do to trigger OFDMA? It will start with something called as a multi-user RTS frame or a request to send frame, which is a broadcast frame that goes across the entire spectrum. So if you're using 20 megahertz or 40 megahertz or 80 megahertz, 160 megahertz channels, that is transmitted as across the entire spectrum, so everyone can hear. Okay? And in that RTS frame, the AP will do some allocation of these tones. Right? So it knows that station 1 has very less information. It knows that station 2 has higher information, and so on. Based on that, it might allocate certain number of tones to station 1, allocate a different number of tones to station 2, allocate a different number of tones to station 3, and so on. In this example that I'm showing, all 4 stations, we have equal number of tones that are allocated, and that information is broadcasted to in the medium. Now, all the stations, the 4 stations that are willing to participate in OFDMA, will listen to this transmission, and they will acknowledge that by sending a clear to send frame, and each of these stations will send a clear to send frame. But the difference here is they will send the clear to send frame in the resource units that have been allocated to them. So station 1 will use the first 52 tones, station 2 will use the next 52 tones, the station 3 will use the next 52 tones, and the station 4 will be using the last 52 tones, right? And so which means that all 4 of them are transmitting simultaneously at the exact same time, right? And so that's what you see here. So all 4 stations are transmitting in their respective allocated RUs, and that is also a confirmation to the access point that the stations are acknowledging that they are going to use those resource units, those tones for their transmission. So it's like the vehicles have decided that they are going to pick the respective lanes on the road, and they've informed that to the access point. Now all 4 of them can transmit on their respective lanes, right? So that comes in the form of CTS. So once that acknowledgement happens, now the AP can send a multi-user downlink TPU, which is basically data being sent simultaneously to all 4 devices downstream in their respective frequency chunks that have been allocated, right? So that this transmission happens simultaneously. And then once that is done, the AP can now send a what we refer to as a block-ACK request to receive acknowledgement for the frames that have been transmitted. And again, this is a frame that is sent across the entire band so that all stations can hear it. And then the stations will send their respective block acknowledgements in the allocated frequency spectrum for them. So again, the same multi-user OFDMA will work for block acknowledgements, and the stations will send the block acknowledgements simultaneously in their respective frequencies. And so and that's how the downlink OFDMA works. The AP sends information, the stations will acknowledge, and this is one transmission opportunity that we see here. The next transmission opportunity can be won by a non-OFDMA station, and that will not do OFDMA at all, even though the AP is capable of OFDMA. That other station will do normal communication, right? And that is just normal. And then you once again you have a transmission opportunity for OFDM transmission, and then you repeat the process, right? So this is how the downlink OFDMA works. If you look at uplink, where the station is transmitting to the AP, the process is somewhat same, but there is a slight difference. In this case, the AP does not know how much information the station has to send. When the AP is sending information, it knows because it's all the data is already buffered. But when the station is sending information, the AP doesn't know how much I could have like 4 different stations. Each one of them could have different amounts of data to send. So the AP doesn't know. So how does the AP find out? The AP sends something called as a buffer status report poll frame, or a BSRP frame. So what is a BSRP frame? It is a poll. The AP is polling the stations to get the buffer status report, meaning the buffer status report is a report that tells how much information is buffered at the station. So the AP will send a buffer status report poll message, which is a broadcast message across the entire bandwidth, and then all the stations that are willing to participate in the OFDMA communication will send their respective buffer status reports, and then once the buffer status reports are received, then the AP will have an idea of, okay, the station 1 has so much buffer data, station 2 has so much data, station 3 has so much data, and based on that information, the AP can do the RU allocation, right? And once the AP does the audio allocation, then it sends the multi-user RTS frame, which is the same as downlink, and then the stations will acknowledge that with the CTS frame. So that part is the same, but at that point there is also a different frame called a trigger frame, because once the handshake is done and the audio allocation is decided, it is not the AP that is transmitting, it's the stations that are transmitting. So now the AP needs to basically instruct the stations to transmit. So then once the handshake is done, the AP will send a trigger frame, which is again a broadcast frame, and that instructs the stations to now transmit an uplink. So now all stations can transmit in the respective audio allocated resource units upstream simultaneously their data, and then after that is done, the block process will continue. So that is how uplink OFDMA works, and that achieves the simultaneous transmission in the uplink. Now, this again, as you can see from this process, it's pretty complicated. It is adding a lot of overhead from buffer status reports, MU RTS frames, and trigger frames. All of these are broadcast frames that are sent across the entire bandwidth at very low data rates. So you can only achieve better performance when you have a lot of data to send, and you have lots of devices that have smaller amount of data to send. That's where you get the most efficiency with OFDMA. Okay, so that's OFDMA. Hopefully that makes sense. And we'll talk about a different concept again, this concept of multi-user MIMO, which was introduced in 11AC. Unfortunately, it was not very extensively used, but it was only downlink multi-user MIMO that was used in 11AC. So what is the basic concept of multi-user MIMO? While in OFDMA, you are trying to get multi-user support by dividing the frequency spectrum into smaller chunks. So you're using the frequencies in a better way. In OFDM, in multi-user MIMO, you're using the spatial diversity. So the concept of multi-user MIMO is that you want to improve spectral efficiency by using the spatial diversity, the spatial nature of the wireless LAN cell. So normally, traditional wireless LAN access point is transmitting as omnidirectional antennas, which are transmitting in all directions in the cell. As you can see in this picture, normally we depict a wireless LAN cell as a circle because the radiation pattern of the signals is omnidirectional, which means that the energy is being equally propagated in all directions in the circle. So this is normally how a standard access point works. But what if the access point does not have to transmit the signals and RF energy towards the client in all directions? Let us say this client is in this direction, and let us say the AP can basically take the RF energy that is transmitting and direct it in one direction towards the station and put all the energy in this direction. And that means that any energy RF energy that's being sent to this station is only going in this direction. It's not going in any other direction, which means that in theory, you could have another station in here, this other side. And if this AP can also transmit to the other station in the other direction, then in theory, the AP should be able to transmit to multiple devices, both this device and that device simultaneously in their respective directions without interfering with each other. That is where you're using the spatial diversity and you are using that for multi-user access, right? So which means that in theory, if you have 4 devices at 90-degree angles around the access point and the signal quality is good, you should be able to transmit beams in 90-degree angles and really talk to 4 devices simultaneously without interfering with each other, right? At a very basic level, that is the concept of multi-user MIMO. Of course, the technology is a lot more complicated than that, but in the time we have, of course, we cannot go through all the details. So that's basically how multi-user MIMO works. And because you're able to simultaneously transmit to multiple devices, you are able to achieve better overall performance. Remember that the maximum net throughput is not changing. So let's say this is a 4x4 MIMO access point, and if you have a 4x4 MIMO client, then there is no need for MU MIMO because he's using all 4 spatial streams and he's using all 4 spatial streams. They're transmitting at the highest possible data rate. But that's not how the real world works. Even though there is a 4x4 MIMO access point, most stations are 1x1 or 2x2. So when the APs communicate with only one device, even though it has 4 spatial streams, because this device only has 2 spatial streams, the net throughput you're only going to get is lot of 2 spatial streams, right? And so basically your capacity is going down. But what if there is one device that has two spatial streams, and there is another device that is spatially in an orthogonal, located in a very orthogonal way, that also has another two spatial streams. And these two spatial streams can use the two spatial streams on this AP, and that two spatial streams on that client can use the other two spatial streams and transmit simultaneously. That is where you have the advantage of multi-user MIMO. But overall throughput is not increasing, but you're able to simultaneously support multiple users, each at a lower throughput, basically. So how does the frame exchange work for multi-user MIMO? So again, if you're doing multi-user MIMO in the downlink from the access point will send something called as a NDP announcement or a null data packet announcement, followed by a null data packet, and that packet is transmitted, a frame that is transmitted, basically it's a broadcast frame. So all the stations, again, only the stations that are willing to participate in MIMO. There will be legacy stations that will not participate. That's fine. Only the stations that want to participate, that will listen to the NDP frame, and then each station will send what we call as a compressed beamforming report, or basically a matrix that represents the channel state, the condition of the RF channel between the access point and the station. And each station that wants to participate will send its respective channel state information in a compressed beamform message, right? So all this channel state information from all the devices is collected by the AP, and once it collects all the channel state information based on the relative orthogonality of the signals. So it will collect all these channel state information, it will do some computations and say, oh, the channel for this particular station is orthogonal to the channel from this station. So I can pick these two stations because they are spatially orthogonal to each other, and I can simultaneously transmit to both. Okay. And that decision will be made by the AP. Maybe there are 4 stations that are sending their beamform reports, but the AP might decide that only 2 are orthogonal, and it might decide to actually beamform to only those 2 stations. That decision is made from this what we call as explicit beamforming, where the station is getting feedback, the AP is getting feedback from the stations, and then from that it's making the decision of how to beam, right? So so that's how the beamforming message information is collected, and once the information is collected, then the AP can decide to transmit to multiple users. So let's assume that there are 3 stations, and there are at least 4 stations, and all 4 stations are orthogonal to each other, and the AP has buffered data, right? It has some data here for station 3, some data for station 2, some data for station 1, and so on. So it can pick the stations from data from its respective queues and simultaneously transmit to multiple stations at the same time. And once that is done, then again you fall back to the normal mode, where you send a block act request, which is again a broadcast frame that goes over in a omnidirectional fashion, and then there is from there again everything is serial, right? Block acknowledgements, receiving block acknowledgement for all the individual stations is all serial in time. So the only thing that is happening parallel is the multi-user data transmission. All of this is serial, and all of this is serial, and all of this is overhead, and all of this is overhead. So the overhead can be very high if this portion is not big, right? So this is one of the reasons why OFDM multi-user MIMO has not been used very effectively, because the overhead can be very high. And especially if the channel conditions are changing very frequently, if the client is moving a lot, then this data is going to be outdated very quickly, which means that you have to poll more frequently to get updated information on the channel. And the more frequently you poll, the more airtime you're using for polling for overhead, and that is more bandwidth wasted, right? So there are lots of fundamental problems with multi-user MIMO, but under ideal conditions, it give you better performance. And then with 11AX, we introduced the concept of uplink multi-user MIMO. So in the case of downlink multi-user MIMO, there was another fundamental flaw, right? When the AP was sending data, let's say it's sending TCP data, right? So all the TCP data frames are going from the AP to the station, but we need to remember that the acknowledgements from the station have to come back to the station, to the AP, and that is uplink. And so there was no MU-MIMO on uplink, which means that the uplink transmissions are all serial. So even though you can send TCP data to multiple stations at the same time, in the downlink, if the acknowledgements are being delayed because you cannot simultaneously send all the acknowledgements, then overall your TCP round trip time will increase, and then your TCP throughput will drop, right? So effectively, for protocols like TCP, it should really be happening with both directions. to actually have some advantage, right? So that is one of the other fundamental problems with Downlink MU-MIMO. So 11AX tried to solve the problem by using uplink multi-user MIMO concept, where you can now do the multi-user MIMO both in uplink and downlink. And it is an interesting way that they do it. Unfortunately, we don't have time to go through that in a lot of detail. But the idea here is that you can use a combination of multi-user MIMO and OFDMA also in a very interesting way. So, for example, all the multi-user transmissions using multi-user MIMO can happen in the downlink, but all the block acknowledgements can be using OFDMA, and they can be transmitted on the uplink in smaller chunks of frequencies simultaneously. So now you are achieving simultaneous uplink transmission, possibly using OFDMA, and simultaneous downlink transmission, possibly using OFDMA or multi-user MIMO. So you can use a combination of these two things and get simultaneous uplink and downlink transmission, which is again, it is very hard to explain, and it's even more harder to implement. So in the real world, most of these things don't work very well. Conceptually, they're great and they're very nice to learn about, but the real world, there are lots of complications for how this is being used. Okay, so that's multi-user MIMO and OFDMA. Let us talk a little bit about a couple of other features that have been introduced in Wi-Fi 6. One of the other features that you probably heard a lot about is what we call as BSS coloring. So again, BSS coloring is something that is very important, especially in high dense deployments where you have a lot of overlapping wireless LAN cells, especially in enterprise environment. So in most enterprise environments, let's say a stadium or a large university or something like that, where we expect hundreds of users, normally the installers will install APs very close to each other, and there's a lot of overlap on the cells. And since you have limited number of frequency channels, you will have channel reuse or channel overlap, right? Because in 2.4 gigahertz, we only have 3 non-overlapping channels. So there will be some form of channel overlap. So BSS coloring will try to make that scenario more efficient. So just to take a simple example, let us say you have one classroom where you have a teacher and let's say some students, and then there's another classroom where you have another teacher and some students. Now this teacher is giving a lecture to these students are listening to that teacher, and then the same thing is happening in the neighboring classroom. So one of the students who is here in this classroom might hear some noise or some voice from the other classroom, but this student knows that no, I don't have to pay attention to that. Even though I can hear that does not belong to the information that I need to listen to. So I'm going to just ignore it, right? And I'm going to only listen to my teacher. And I also, when my chance comes to talk, I will also talk. Even though I can hear some interference from the neighboring classroom, I'm just going to ignore it, and I'm still going to talk, right? Because I know my teacher can still hear me. So that's basically the idea behind BSS coloring. So what the concept really here is, you can assign a color to each wireless LAN cell, right? And the color is an abstract concept here. It's not really a color; it's a number that is assigned to each AP. And to explain it in an easy way, we're using the concept of color. So let's say take this example here, and you have one AP1, which is on channel 36, and let's say the installer of this network assigned that color blue. And there's another AP somewhere here. It's also on channel 36, AP2, and that also has the color blue. And then there's another AP somewhere far away that's also on channel 36, that's AP3, that is assigned a different color. So the idea here is, if these two APs are close to each other in space, then we can assign the same color, which means that we are assuming that they're the same contention domain or collision domain. But there could be a different AP on the same channel, which is a little bit farther away, which is falling beyond your signal threshold, and you can assign a different color to it. So now this station, let's say this station wants to communicate with this AP, when it senses the medium, if it sees any WLAN frames, it will go and look at the physical layer header, and inside the header, it will see what is the color of the frame. So now in the HE signaling fields, now you have this new field called BSS color information. Right? So now when you actually go and see a signal on the air, when you want to transmit, you're doing carrier sensing. When you're doing carrier sensing, you see some wireless LAN signal, and when you decode the signal in the HE information element, there is the color. And if the color says that it is the same color as the current API that you're connected to, that means that you are in the interference zone, and so you need to back off, and you need to detect that as a valid. So the idea here is when the station wants to transmit, and it will look at the color information inside when it's detecting signal, and if it's detecting a signal from a neighboring cell, then it will look at the HE information element inside the physical layer header, and it will check if it's the same color. If it is the same color, then that means that it is indication that it's within the interference zone, so it will back off, it will not transmit. But if that signal that is detected is from a different color, that means that the system is saying, yeah, you can hear the neighbor, but it is okay. The signal should be very low. You can still assume that it's below the threshold and you can transmit. And this allows for better use of spectrum, especially when there is reuse of channels. So that's really what BSS coloring is. And each AP, when you're installing these APs, if it's 11AX AP, you in the configuration you can assign different colors based on how you want to manage the frequency reuse in the wireless LAN cell. So this allows you to create multiple APs with same channels, but still create independent contention zones. So that's what BSS coloring is. Target wake time is another feature that has been added, and the idea here is that if those of you who know legacy power save, basically the concept of power save is really controlled by the access point in legacy power save. So if the AP has data to buffer to transmit, then the station, if it wants to go to sleep, it can actually send a PS poll message or a null data packet with the power save bit set and indicate that it's going to go to sleep to the AP, and then the AP can start buffering data, and then the AP will indicate in the beacons if the station has buffered data, and the station is supposed to wake up at regular intervals and check inside the beacon if there is data to receive, and if there is data to receive, the station will wake up and then will receive the data. So the station is heavily dependent upon the AP to go to sleep and wake up, and the wake up sleep cycles are depending upon the beacon periods. So let's assume a scenario where there are two stations that woke up, and the AP says both these stations have data to transmit, data to receive. Both the stations have data buffered. So then both the stations have to stay awake. While station 1 is receiving data, the other station is not receiving data, but it has to still be awake because the AP has already told it, hey, you stay awake because you have data. That is inefficient use of the battery life for the second station. The station is now at the mercy of the AP to decide when to go to sleep and wake up. And that was seen as a basic flaw in legacy power save. So technologies like TWT will basically, at a very high level, allow the AP, the station, to take control, and it's allowed to trigger or at least schedule the sleep time. So now the station can negotiate sleep times with the AP irrespective of the beacon period. So you don't have to wake up at beacon intervals. You can wake up as per your schedule that is decided between the AP and the client, and based on the schedule, you'll wake up or you go to sleep. And that is at a very high level what target wake time or wake time is. I know we don't have time, so I'm not going to go into all the details, but that is what this feature is. So just to summarize here, 11AX has added higher throughput in the form of 1024 QAM, but again, that really only works when you have very good signal quality. And a lot of other features about 11AX are not necessarily about throughput, but about higher efficiency. How can you use better use the medium? How can you get better spectral efficiency? How can you get better frequency reuse? Those are the features. We talked about OFDMA, Uplink, Downlink. We talked about multi-user-MIMO. We talked about BSS coloring. We talked about target wake time. So that is it for this session. Hopefully, it was not too confusing and you found it useful. And in the next session, we'll go into Wi-Fi 6E or 6 GHz spectrum, which is very exciting. Lots of cool new features that came with 6 GHz, and we're going to talk about all of that in the next session. So that is it from my side. So these are some references, and the slides are posted. There's lots of good videos and white papers on 11AX that you can read. I posted some of the links here.